it's an honor to introduce Dr. Mike Hinds. He's a highly respected good delivery consultant for the London Bullion Market Association, bringing over 30 years of expertise in precious metals assaying and refining. Beginning his career as an assay chemist at the Royal Canadian Mint, he developed mastery in advanced analytical techniques such as mass metrology and X-ray fluorescence spectrometry. Dr. Hinds has played a pivotal role as chair of the LBMA Reference Material Project, which was instrumental in creating the first industry-accepted fine gold and silver reference material, now widely used by analysts world over to ensure assay accuracy and standardization. His contribution extends organizing and supporting the LBMA's biannual Assaying and Refining Conference, a key platform for industry professionals to exchange best practices and ideas to elevate assay and refining standards globally. Dr. Hinds is also deeply involved in ongoing initiatives to produce certified reference material for validation of assay methods and planning educational resources like a modern textbook on fire assay. He continues to offer consulting services, emphasizing on enhancing assay accuracy, compliance framework, and technical collaboration across the precious metals industry. Ladies and gentlemen, request you with a resounding round of applause, welcome Dr. Mike Hinds.
I'd like to thank the organizers for their kind invitation, and particular Pankaj Deshma and Ankar Goyal from MTC PAMP for their promoting me as a keynote speaker. It's been great, and I hope we can all learn something about X-ray fluorescence. I've developed a dangerous amount of knowledge about XRF over the years. I can get myself into trouble and hopefully get myself out and get the right answer. And I hope we can, I help you do the same. I do have to acknowledge the LBMA for supporting my travel here, and also the material I'm presenting to you, I did not develop alone. I'm part of the London X-ray Consulting Group, who I collaborate with Alexander Seyfarth in the US, Maggie Lobster in South Africa, and myself in Canada. And by the way, the London X-ray conference was actually London, Ontario, not London, England, where we developed this course. So, but we had to call it ourselves something, so we decided that would be the group. But so I'm indebted to my colleagues, both in the LBMA and from a London X-ray Consulting Group, to provide you with this presentation. What is XRF? Talk to you about the physics. Can everybody hear me? Yes. Talk about the instrumentation in terms of, there are two flavors of instrumentation: energy dispersive, which I believe most of people in this room are more familiar with, and wavelength dispersive, which are a much bigger instrument, more high power. Of course, X-ray comes with its own challenges in terms of matrix effects. We'll talk about that and how they can be overcome. We'll talk about calibration and matrix correction methods to overcome those matrix effects. And then we'll talk about applications of precious metal in terms of quality control and some method examples. So that's sort of the plan for the day. We'll see how we get along. At any point, if you're missing something, please ask me, because if you're missing it at the beginning, you're going to get lost fast. And if you've gotten lost, somebody else has gotten lost too. So please ask a question. This is for your benefit. And I hope we can help each other with this process.
Excuse me?
Yes.
The complete presentation will be mailed to us because we don't have a facility to take notes now.
That's right. You'll get a PDF of this electronic version.
Yeah.
So that you don't have to worry about taking notes.
Yes, yes.
Okay. Thank you.
Okay.
All the sessions of the day.
All right, so what is X-ray fluorescence? Well, it involves, in the red, incident radiation coming in with sufficient energy to kick out an inner shell electron. And we see this in red, this electron being ejected. Now that leaves a vacancy, and the atom is energetically unstable. So we want to have outer shell electrons relax into that position. So in this case, we have the green, from the L shell relaxing into the K shell, and that in doing so, it releases an X-ray. And that's what we measure. And this is a K X-ray, K alpha X-ray. In the other cases, we have an M shell electron that has the possibility of relaxing into that position as well, and that is where we'll get a K alpha or K beta X-ray emitted. Different energy, but you should see both energies in your sample if they're there. If you see a K beta, you think it's a K beta and you don't see a K alpha, you've made a mistake. So they all have to come together. So that's what this process is. So we have to have incident radiation to kick out an inner shell electron, and then everything will relax in to form, to give you emitted fluorescent X-rays that you then measure. So what information can we gather from XRF? Well, the element is identified by the energy of the emitted X-ray. So silver K alpha, we see a 22.16 keV. That's a measure of energy that we use in XRF to talk about that. So if we see something at 22.16, probably silver. Gold L alpha is at 9.17 keV. That will tell us that gold is there. And the concentration is calculated from the number of counts that we see at each of these energies. And we can relate that back to a concentration. And those are the two bits of information you can gain from XRF. And in terms of counts per second, KPS, or CPS, or kilocounts per second, if you're depending on the more signal, the better, basically. All right, the advantages is it's non-destructive. We don't consume the sample. I mean, we have to change it a bit to get it inside the instrument. So in that case, we have to alter the sample a bit to get it in there. We can do solids, powders, and liquids, and in some cases gases, but I don't think this crowd is that well. Yes?
The first one, non-destructive, when you say for XRF, we need to prepare the surface without which you cannot.
Yes.
So how do you call it non-destructive?
Well, compared to ICP emission or ICP mass spec or flame, you have to dissolve the sample. It's gone.
Okay.
It's not in the same form. So it's non-destructive in that percent. You still have to do surface preparation and cast it in the right form to put it into the X-ray.
Yeah, that's what we normally have it, because there are a lot of hallmarking centers across the country in India. The jewelry which comes to us is finished jewelry. There's no space to even scratch it also.
Yes.
And that is why the results basically show something more, because all that jewelry basically they are polished with 24 karat solution. Yeah. So actual purity basically reflects, the XRF does not reflect the true purity.
Well, we'll get into that. That's related to surface finish. And your samples and standards should have the same surface finish to be comparable. If they don't, then you're not going to have the same.
Yeah. So practically for the bulk analysis, this does not help. It's only for the random, like you say, the melt sample or some strip preparation. But for the bulk analysis, like we see jewelry, XRF is I don't know, it does not give a proper results because of the surface.
Again, that depends on whether it's curved, straight, or flat. You have to, there's limitations to that. It works best if you have an aperture that's completely full, flat. That is a limitation.
Yeah, because we had that Birmingham SO office that introduced where that only XRF based on that they do hall marking.
Yeah, yeah, and I think that's where you have to develop standards that reflect with the same surface finish and shape as the things you're trying to have. And that's a challenge.
Thank you.
We go from boron to uranium. The accuracy depends on the standards. We just talked about that, surface finish. Precision depends on the counts and the counting. So within analysis, matrix effects are there, but they're predictable and we can correct them. And the instrument is very stable. The X-ray comes on, it comes up to the same power, the emission level, pretty much all the time. And you can correct for any drifts with that, and we'll talk about that later. But overall, it's very stable. Versus some other instruments like a flame AA or something, it all depends on how the flame is going and how you set it up. So compared to other instrumentations, it's incredibly stable. There are disadvantages in terms of matrix effects. There are inter-element effects. There's particle size effects. There's mineralogical effects. There's chemical effects, which we with precious metals don't have to worry about. Thank goodness. But that last one we really don't have to worry about. But those are things that we have to worry about and be concerned with. There's a limited penetration.
Is it recommended to do the XRF analysis on liquid sample? Because
Depends on what liquid sample.
suppose gold chloride solution is there, and if you want to do the XRF on that, so is it recommended that result might not be accurate because some suspended solid particles will be there?
That's exactly
Yes.
Suspended particles
Yes.
that could be there. You also could have failures of the film, and that will destroy your instrument.
Okay. Okay. Yes.
So you can do it. A lot of terms and conditions apply.
Okay.
And so, you can't. I wouldn't say it's recommended. People can do it, but there's other instruments like an ICP or a flame AA that may do it better.
Okay.
And with less problems. There's a limited penetration depth into the sample. The depth from which your photon escapes is a very important factor. We'll take a look at that later, which is wavelength and element and wavelength specific. Depends on what element you're looking at and what the matrix is. No low atomic number analysis like hydrogen, helium, without specialized crystals, but we really, for most of you are doing EDXRF and not interested in these elements, so it really is not too much of a disadvantage. So, in overall, there are 5 steps to a good analysis. There's the sample preparation. Well, first of all, even before you do this, you have to do a proper sampling, representative sampling, so that it does reflect the bulk. Then you have to have a sample preparation step. Then you do have to do excitation of your characteristic lines. It involves an X-ray tube or a power and a power supply. Then you generate your secondary fluorescent spectrum. It's either through a crystal collimator system in terms of your wavelength dispersive, or a pulse height analysis detector, which is your energy dispersive. You have to detect that. Then you have to measure and get the readout in terms of counts per second for that. And finally, then you have to convert your X-ray intensity data into analytical concentrations. And that way you have to have a calibration curve, and you have to correct for matrix effects, and get a net intensity, not include the background for that. So those are the things that we're looking for in your X-ray equipment and your process. So in terms of kinds of spectrometers, sorry, my animation got ahead of itself. There's wavelength dispersive, there's sequential systems, there's simultaneous ones, and which are quite big, about the size of a washing machine or more, and then it can be miniaturized to a benchtop system but at lower power. And then we have our energy dispersive ones. We can have benchtop systems or handheld systems. We can combine energy wavelength dispersive and energy dispersive ones systems into one instrument, and we can combine XRF with X-ray diffraction. And this is very popular in the cement industry, but not particularly useful for the precious metal industry. And there's total reflection, which is another technique that we're not going to get into, but it seems to, with solutions, you can draw the sample and you have a monochromatic or a mono layer, and then do the X-ray measurement there. And then we have the instruments that have gone to Mars. And it's really an out of this world application. So the instruments have been customized to look at things in the geology on Mars. So there's lots of things we can do. Let me first of all talk about energy dispersive systems. Just a quick overview where we have a tube, an X-ray tube, goes through some filters, interacts with the sample, and the fluorescent goes to a detector, in this case a silicon pin detector, which is a more older slide, goes to a preamplified amplifier, and then we get a spectrum that measures the pulses and the instruments from that experiment, and then we can convert those to a concentration. So that it's a very simple system, so that we can have a handheld or a very simple benchtop system. I think most of you are familiar with that. On the other hand, we have a more elaborate wavelength dispersive system where we have a more powerful X-ray tube impinging on the sample. We go through a primary collimator to make parallel lines, X-ray lines. We bounce that off a crystal, and then we have a detector here. And each element is measured sequentially in that process with much higher count rates. And that's where we can do a very good job on trace elements. So, these typically have a larger, bigger footprint, so they can accommodate a larger auto sample. So those are the two flavors of X-ray fluorescence. But before we get onto that, we'll talk briefly about the physics of XRF. And that's in terms of the energy of the X-ray, conversion from energy to wavelength, how X-rays interact with matter, the process of X-ray fluorescence, and we have a concept of excitation potential. You have to have sufficient energy in your exciting wavelengths, or energy to excite the fluorescence in the sample. If you don't, you're not going to do the experiment. Then we get characteristic X-ray fluorescence, and then we also look at tube excitation conditions. So what are X-rays? This is in the range of 10 to the minus 5 to 100 angstroms in that energy range, or wavelength range. So for barium K alpha, which is gives a very intense signal, it's very highly energetic, it has a very short wavelength, but energetically it's around 32 kilo electron volts, which is a measure of the energy that people use in terms of, it's a convenient term that people use for X-ray fluorescence. On the other hand, we can look at fluorine K alpha at 18 angstroms, a much longer wavelength, which means it's very, and we also can do measure this in terms of, express this in terms of nanometers, and it has a very low energy, 0.68 keV. So that's the spectrum that XRF covers. And in some cases we could do boron if needed, but a lot of boron is on some of the materials that make up the X-ray tubes in the first place. So it's a lot more difficult to measure that. So that's the energy range we're talking about. And in terms of this slide, the thing that you have to, I like to draw your attention to, is that this expression energy, the conversion of energy to wavelength to energy is done by this expression where we use Planck's constant multiplied by the speed of sound. So the thing to watch out for here is that the wavelength and energy are inversely proportional. So that's just letting you know that the two are inverse. So in terms of X-rays, we can do a lot of things with the X-rays. If we have this red incident beam, if the material is thin enough and this is high enough in energy, it can go right through the material. And that's the basis of our X-ray, medical X-rays. But we can also have fluorescence, where it can excite inner shell electrons, and we get relaxation and generation of fluorescent energies. That we can do. That also happens during your medical X-ray. We can have scatter, where it can bounce off the material and have the same energy as your incident beam. Or we can have what we call Compton scatter, and some of that energy is lost and we get a different energy out. And we're not going to get into that because we don't have enough time. And generally for precious metals, that's not a thing. We don't get Compton scatter because you get that on lighter materials, not with gold. So in terms of energy fluctuations, this is for titanium at a Z or 22 protons. So we have an inner excitation that kicks out an electron from the inner shell. Then we can have two things happen. We can have an L shell electron relax into that position and gives us a K alpha wavelength from that, or X-rays with that energy, or we can have an M shell electron relax into that position and we get a K beta. And that's a little bit higher energy because it's a higher, it's a greater distance away so we'll get more energy out of that. So that's how we get KL, the two types of K radiations out of there. L lines come when and this all happens all at the same time. So we have energy sufficient to kick out an L shell electron, and then we have an M shell here relaxing into that position, and that will give us an L alpha line. A further electron in the N shell can relax, and that will give us an L beta. And the reason now all this is happening at the same time. It's not a sequential thing because there's so many photons going through. This is all happening at the same time. And if you see a K electron or K alpha radiation, you should see a K beta, you should see an L alpha and an L beta, all at the same time. If you don't see any of those, you've made a mistake in your identification. The characteristic line spectrum, atoms, here we have characteristic line spectrum. When we bombard the sample in the X-ray tube, we get the target are bombarded by high-speed electrons. These electrons then expel an electron, and if they have enough energy, we have an excitation potential is the minimum tube potential required to expel an electron. This is within the exciting tube, and it's very important that we have to have that enough energy to do that. And here are some examples of potentials in KeV in terms of energy. We start with sodium. For K alpha, it only requires 1.1 keV to generate fluorescence, whereas as we go further higher more dense elements, a higher Z number, we get to gold at 79. We have 80.7 keV required. We don't make tubes that do that, so we can't excite the K lines in gold. However, we can excite the L lines, and that's why, and we have that limitation for gold. Silver is not a problem, but we have to be aware that there are excitation potentials for each element, and we have to have sufficient energy to excite those elements to kick that inner shell electron out to evolve a fluorescent X-ray. These are excitation potentials. Again, we've talked about that. I just draw your attention to gray line. These are not excited with the X-ray tube technology. However, they are looking, there is a movement afoot to develop a higher energy X-ray, and if people are interested in helping develop this, they see me and I'll put them in touch with the right people. If we can induce K-shell for iridium, platinum, gold, and lead, then we get a lot more information, and the X-ray measurement would be that much more sensitive for these elements. We'd get a lot more counts on that. So as a result, but otherwise we have to rely on the L shell for those elements. So in their X-ray tube is that you have a cathode. There's a high potential between the cathode and the target, and electrons, there's a heated coil, and it's bleeding off electrons that are being slammed into this target anode, and it's generating X-rays that go to the sample. That's what's happening inside your X-ray tube. This is a side tube. There are end tubes which do the same thing but with a different geometry. But essentially, this is what happens. So from here, we get two types of radiation. We get Bremsstrahlung, meaning breaking radiation, because these electrons are slamming into a target, and they release a spectrum of X-rays because they're being stopped. So that gives, and we'll see that in a minute. So there's Bremsstrahlung radiation, and then because it's a metal target, you're going to get the characteristic lines, X-ray lines, from that metal. For example, rhodium is a common tube material. So you will get the rhodium lines on top of the Bremsstrahlung radiation. We'll see that in just a minute. So this is the continuum, or also called Bremsstrahlung radiation, where you have your primary X-rays, electrons from the tube interacting with the metal of the anode. Some will glance through the outer electrons and will generate very little, some radiation. Others will interact more strongly with the nucleus and generate a lot more intensity from that interaction. And this continuum is used to excite fluorescence in your sample, because on the bottom is the energy. There was still, most of the energy in this case is around, for the continuum is about 11, 12 keV, but you also get energy 30, 40 keV that will excite other atoms in the sample. We can change this a bit by changing the keV in your X-ray tube. We start with 10 keV, we're not going to get much out of that. And we go to 20, 30, 40, 50. Most of the energy dispersive X-rays, such as this are about 50 keV max. And we can do an experiment later to show what happens with the counts as we increase that. The other option you can do is change the current going through the X-ray tube filament, and that will change the intensity. Given, in this case, we set the intensity, the energy, fix the energy, constant keV, and change
the current going through the filament, and we will get more signal, intensity of the signal, as we increase the current, because we're really pumping through more electrons through the system. All right, so you can have those two variables to change your excitation. And as we talked about, this is an example of the X-ray energy distribution from a silver X-ray tube, which is common in many of these energy dispersive tubes, or palladium, sometimes molybdenum. I think in this, it's molybdenum? Yeah, thank you. So in all these things, you're going to get your continuum that will do the majority of your excitement. And if you're lucky, you can have, you will have an X-ray tube with these very strong lines. And if you can have your sample being excited by, if the elements you want to have excited come close to this, then you're going to get a lot of excitement, a lot of signal from that. So you have the two aspects to help you excite the X-ray fluorescence within your sample. We haven't even this is all within the X-ray tube. We haven't done anything about the sample yet, okay? This is just what's coming out of the X-ray tube. One other thing I'd really like to point out to you is that there's relative intensities of all these X-rays. Within the K series, K alpha 1 is, if we could normalize it to 100%, K alpha 1 is 100. K alpha 2 is about half of that, or 50%. K beta 1 is about 15% of K alpha 1, and K beta 2 is 5%. However, in many cases, we can't resolve the two, K alpha 1 and K alpha 2, because we don't have that resolving power. So they come out to, these two combine and are really about 150 together. And then we have a combined, it's slightly skewed. For the L series, we have L alpha 1 being about 100. We can resolve L beta 1 about 80% of L alpha 1, L beta 2 is 30, and so on down. M series, we have, again, this type of alpha 1, alpha 2, they're both about equal to each other. However, the big thing is K series are about 10 to 30 times higher than the L series in terms of overall intensity. And the M, they're down around 1%. So analytically, M lines are not that useful to us. What are useful to us are the K and the L. And it's just a question of which ones we can use. Luckily, there are very few interferences for precious metals. If we were measuring other things like lead and arsenic, there are some overlaps. And there are still overlaps within other elements, depending on their combination of elements. So we'll talk about that a little bit later. Any questions about this? Everybody's okay. So in terms of the types of spectrometers, we have our energy dispersive and our wavelength dispersive. Generally, the energy dispersives are smaller, whereas the wavelength dispersive ones tend to be larger and require more power and are less portable. Common features for all XRF measurements is you have to have an excitation source, you have to have a detector, you have to have a signal processor to then use that to convert that into a usable signal and do the calculations. However, you also have to have, it's a comparative technique, and you have to have samples and reference materials that are homogeneous, that fill the aperture to give you your best results, that are flat whenever possible, and your reference materials have to have a known concentrations, have a certificate that gives you a value, plus or minus an uncertainty, and whether it's a standard deviation or 2 times the confidence interval. Yes?
Do you require certified reference material for calibration of these equipment or reference material?
I don't. There's nobody, you have to decide whether you want that or not.
Now we have a typical problem in India
Yes.
that auditors normally insist on XRF also being calibrated by CRM, which is impossible
Yeah.
probably.
Yeah.
To use different CRMs of different auditors are not available.
Yeah.
And again, why CRM when you have reference material which is basically known composition?
Yeah.
I've done fire assay a number of times. There's
Yeah.
a one I'm using it for.
Yeah. Here's a distinction. There's a reference material that you have done in-house and you have confidence you have that.
Yeah.
That's one thing. A certified one as an outside national lab or certifying body has get together many different labs and done some work on it.
And again, because XRF basically what we are using is only to say the homogeneity or probably approximate purity.
Yeah.
We are not giving issuing any certificate for the
Diplomat-
metal content.
Yeah.
So why CRM is being, I mean this particular
Yeah.
topic will help, I think probably the people who are sitting at the auditing level,
Yeah.
they insist that you should go for, even the standards say that you have to use CRM for
Yeah.
XRF.
All right. Here's the thing. If you can, it would always, in the ideal world, you should have them. Practically, they don't exist for everything. But if you can get one, then you can use that as a comparison to some of the other ones and help you certify your own one. That is one possibility. The XRF police worldwide will not arrest you if you don't have one, but it's more, the better standards you have internally, the better results you're going to get. So it's really what's available to you and what you can, the time and effort that you can spend to get that. The more you can invest in that, the better you're going to be. And if you can cooperate with other people, then you can develop a certified reference material. Let me put it this way. Technically, the LBMA reference materials that were developed in 2009 are technically not certified reference material because there was not a certified body, national body making them. But
No,
everybody's
that's
using them
exactly what
because that's the only thing available.
ISO 17025
Five.
basically when it comes to metrological traceability.
Yeah.
And that is for something which are reference material which are using for XRF.
RF. You can still have them traceable because they're all traceable to a mass standard.
Yeah.
So long as your mass standards that you use to do fire assay or whatever are traceable to the new definition of the kilogram
Okay.
as of 2019, you're okay.
Planck constant.
Yes, through Planck's constant, exactly.
Thank you.
Does that answer your? I'm afraid
No,
that's the
okay.
best answer I can give
It's
you.
a topic which is basically harassing a lot of people are being harassed only because of this reason.
Yeah.
RM reference material as such, it's a CRM.
Yes.
It's not possible for anybody to just have it
Yeah.
CRM.
And that's where if you can combine with your other laboratories to do an interchange and make your own, then you're
Yeah.
that step up.
Yeah, we have auditor sitting.
This is how it develops. Good point. I mean, excellent questions, excellent observation on that. Energy dispersive spectrometers. We've seen this slide before. It's a very simple setup. Tube, in this case, a filter, if you need it, a sample, and a detector. And they have to be offset so you're not analyzing the same radiation. So that's the basic setup. It's relatively simple, and most of you have. It is, I think, the more prevalent XRF in the precious metal industry in India. Am I more or less correct on that? And this can be miniaturized further to the handheld, where you have an X-ray, you have a detector, a signal processor or CPU, and of course the sample. You still have a filter that can be put on the front of the X-ray tube. So it's all very tight. It will be battery operated, so the X-ray source is not going to be as powerful as what you have with a plug-in here, but it can still work. Certain terms and conditions apply. It depends on how long you're going to hold it and whether you're shaking or not. Lots of other things. Most people use handheld XRF for a sorting just to give you an idea, is it past this point or no? Am I going to settle with a handheld XRF? Atoms in the sample are excited by an X-ray, and on my computer, I would hear a zapping noise. So this generates atoms by emitting a secondary electron. This is our favorite slide showing fluorescence X-rays being generated, then are collected by a detector, and then converted to a voltage pulse to its energy and combined into a spectrum. The peak intensities are related to concentration or thickness. So we have excitation, detection, pulse processing, spectrum, and your results. That's every XRF does this, but in the context of energy dispersive, that's what's happening. Okay, so this gives a simpler version where you have your X-ray, there's a filter, the sample, and you're going to detect it. So again, it's a bit of repetition, but what we want to do is we want to suppress the undesired parts of the spectrum. And we can do this by a filter. So in this case, we have a titanium filter there that stops any X-rays below that. They're not going to excite the sample. Some bits of the sample that the spectrum that you don't want to measure, they're not going to be measured. And only the higher energy bits will be. So we can do that. And this is an example. The energy dispersive X-ray collects everything. So in the black, no filter, we see this is a silver anode, so we get all the silver lines, which aren't useful to us because they come from the X-ray tube. That's not part of the sample. So we don't want that. The X-ray, the detector will take everything. And it can only count so much. And if you're going to fill it up with background, it doesn't have a lot of room to count the bit that you want. So we use a filter. In this case, the blue is the aluminum filter, and it removes that whole bit of background and tube spectra that we don't want. And we'll measure the blue part of the spectrum and get that information. We can count longer and get higher counts for that, and we won't saturate the detector. Similarly, we can use a tungsten and aluminum filter, which is depicted in the red. It really knocks down the background, and the signal then has a much higher signal to background ratio, and it ends up being a better way to measure the sample. So we can do some things with that. Yes?
Yeah, is this foolproof? Means there will be no interference?
No.
It will be?
No, it means that you've just eliminated the bits that you don't want.
That's right. But to the extent of technology, but is there possibility of any interference which
Yes.
can be also accumulate with this and
It
give some
depends what
false
filters
result?
you have.
Pardon?
It depends what filters you have
Yeah.
and what the interference is.
Other way I'm asking.
Yeah.
Do you think any other element can interfere in these spectrums?
Yeah.
Which is not known?
Yeah, and we'll get to that in some of the other slides.
Okay, because
This isn't a precious metal slide. This is something else. And it's just illustrating the purpose, what the filter does.
Okay, means
Okay.
you are thinking that sample will not have any other things, like these things are there only, and very minor elements which is known to you
Yeah,
already.
yeah.
So that only you are taking out of from the
All-
filter, by filtering.
All I'm just showing you is what the filter does. Not saying anything about interferences from the filter. You want to, the limitation on the energy dispersive is you collect everything. The bit is you want to collect the focus on the part of the spectrum that is important to you. And your filters can do that for you. If there are interferences, then you can measure them and correct for them. There's
That
a
is
way-
possible.
It's
Present
possible.
technology, that is possible,
Yeah.
right?
Yes, we'll come to that in the latter part.
Okay,
Okay,
thank you.
yeah. So we have your detector, which this is what it looks like. What is important here is, I'm not sure that I can do the animation on this one. Anyway, we'll move on because it's fairly technical. The bit here is that you're going to get a pulse height reading. You're going to get a low peak, a high peak at different times, and the pulse height depends on the energy. So we can then count these pulse heights correspond to different energy bins, and we can build up a picture, and then we can get intensity here, basically the number of times we count that energy, and do some signal processing and get peaks out of that. That's how it works. Putting it all together, you have a spectrum like this. This is at the low keV, so we're getting silver L alpha, palladium L beta, all overlapping. And we have a big background. We can mathematically, you can do deconvolution and separate out your background and get rid of it mathematically. And then you see the gray? The gray is your spectra that you collect by the spectrometer. You see the black line here? There's a gray and a black line. The black line is a calculated value to fit that curve. And that's where we're going to get our intensities. And for example, if you notice that we have a silver K beta 2 here, and we have overlap between a silver L alpha and a palladium L beta, I can use that ratio. I can measure that very well, and I can use that to separate out that interference between the L alpha and the palladium L beta if I have a free line. I know what the ratio is. We know from a previous slide what our intensity ratio is, silver L beta 2 to L alpha. We know that, so we can predict what the silver L alpha line is and subtract it from the palladium interference. So that's what we can do to minimize overlaps and interference. I hope, does that sort of answer your question? If you have a free line from one of the series, you can make some of those corrections. And again, you can have standards that will help you as well to make that, if you have, there's some techniques there. All right, energy resolution between the peaks. Silicon drift detectors have a resolution of about 0.125 to 1.14 keV. This is for magnesium at this wavelength. This is the way this is a standard way of expressing the resolution. So if we have K alpha lines here, rhodium, palladium, silver, and cadmium, we see the energy of these lines, and the energy dispersive X-ray can resolve those no problem. Resolution depends on the concentration, the total counts, the detector, and the deconvolution software. But overall, these should be relatively easily resolved. If we get to L alpha, or this lower energy range where we have gold, we see copper K beta 1, iridium, L alpha, gallium, platinum, zinc, that are all coming very close to these, and it may not be possible for your detector to resolve the peaks because they're so close. And again, it depends on whether the elements are high concentration or low concentration, the total counts, and it does depend on the deconvolution software of your spectrometer. Some are better than others. So we don't know whether that will resolve them, but it all depends on what's in your sample. So that's why the dirtier your sample is, the harder it can be to deconvolute. If you're looking at a jewelry alloy in your factory, you know it's a certain composition and it only has silver and gold, then you don't have to worry about these interferences and you can resolve them. But if you're dealing with mine doré, that's a whole nother story. All right, so we've talked about the data flow, and again, it's the same thing. You will get a spectrum that's very complicated. We can resolve that by deconvolution to just the essential peaks. We get intensities in terms of counts per second, and then we can convert those to element conversing. In terms of an energy dispersive program, you optimize segments for element groups. Because you take the whole spectrum with filters, you can isolate sections of that spectrum, and I call this semi-simultaneous. You can reduce the background, optimize the signal to background for each, and you can take a look at your detector counts across the entire spectrum and optimize your groups. I think we're going to go into the more practical things right now and begin to talk about that. So one of them is infinite thickness. So it's the amount of fluorescence from atoms at the surface greater than the fluorescence from the atoms deeper in the sample. So basically, you can't, at a certain point, you can, deep inside the sample can't escape. They're going to be generated, but they'll be absorbed before they even get out. And that's the thing. So that's, when this occurs, the sample is considered infinitely thick. And that's where most of you want to be working with your samples that are infinitely thick. Generally determined for the most energetic element that you've got for determining what your infinite thickness is. So in terms of the sample, you have, this is your exciting fluorescent energy going into the sample. It can go quite a ways into it, but the fluorescent from your element can't get out. If it comes out and doesn't escape, at that point it's considered infinitely thick. And we can calculate that. What we want to indicate is that your analysis depth is less than your infinite thickness. And that's really what this next section is all about. Depends on the energy of the analytical element that you're looking at, like whether it's a K alpha or L alpha, and you want to determine it for the most energetic element. It depends on the matrix composition. The more dense the material, the lower your becomes less. And this is an example of your infinite analysis depth. If we take a look at low energy, it's silicon K alpha. In steel, in blue, red is glass or stone, and plastics or wood, which is lighter. And we can see the lighter the material, the greater the analysis depth. And of course, as we go up in energy, silicon K alpha, which is quite energetic at 25.3, you're going to have a much greater analysis depth. However, for gold, it's somewhere in the middle, and the energy, you're only looking at a very small depth between somewhere around 6 microns. That's your escape depth. And that's in steel. So that gives you a sense that you're really not looking to, this is a practical point. This is the analysis depth of gold L alpha in gold metal. You're only looking at about 6 microns. The width of a human hair is 75. Silver K alpha is much more energetic, more than double, but it's only 16 micron in gold. If we went to a silver matrix, it's a little bit greater for gold L alpha, 16, still not very much. Silver K alpha is, again, quite good, but it's only twice the amount of a human hair, not much. And if we were looking at copper, it's really close to the absorption edge, and it's not all that great. And we haven't talked about absorption, so I'm not going to talk about it. If we consider the mass of gold analyzed in gold and with silver and gold, in gold, and we consider the aperture of your X-ray at 2 millimeters, 5, 10, so on, and consider a cylinder of that diameter and that thickness, remember from the previous slide, with these depths, how much mass are we really interpolating? Well, for 2 millimeters, you're only looking at that amount of gold. For silver, you're analyzing, at that wavelength, you're analyzing a little bit more. At 30 millimeters, or about a 15 millimeter diameter, you're approaching what is going on with fire assay between 0.2 and 0.5 grams. So for small spot sizes in chains and things like that, you're looking at very little material. And that's a practical problem. So you want to make sure you're looking at something that's not curved, flat, and you can cover the whole aperture and doesn't have any bubbles or anything. You'll have a better chance of doing it. I also suggest that you do it multiple places, not just one spot, because you're not looking at much material. All right, this is just, and if we look at infinite thickness, how much sample? It's only slightly more. We were at 6 for gold Now for infinite thickness, it's 9.1. It's the difference between infinite thickness and your analysis depth is very small. Everything is small. So for infinite thickness and your analysis depth for the determination of many precious metal, it's very small analysis depth or infinite thickness. Lower energy lines for L alpha gold. If we could get K alpha gold, we would have a much greater analysis depth, but we're not there yet. There's a limiting on determining in plated materials with precious metals because of that small depth. So you're not going to do that. In metallic samples, mass interacting with X-rays is small. Your samples have to be homogeneous at that level, and your standards have to be. Otherwise, you can be fooled. You may take, you may have to analyze more than one area and average them to get a better idea. Yes?
I have one more question once again. When you say analyze more than one area and average, more than one area means how many? 2, 3, 4. And second question once again is to hall markers. How many areas? Is there any standard maintained by Hall Marking Association for how many areas they have to do? Is there any audit which the Hall Marking Association does for various hall marking companies? And are there any adverse results of such audit of hall marking? I once again...
No, those are great questions that I can't answer.
Yeah, so I would request that if those questions can be addressed here.
Yeah.
So when, sir, you are saying analyze more than one area,
Okay.
what is the standard issued by BIS on analyzing more than one area? And whether the hall marking centers in India are actually doing that?
Okay, let's ask, is there someone who can answer the first question?
Yes. I think those answers should be given.
He is covering all these hallmarking related problems. Hallmarking is not his area. We need to consider that he is an expert on XRF. He's not from technical expert for XRF area, not hallmarking and all these things. All your questions on hallmarking will be answered in the second half, where Mr. Chandan Rao is there, who is from BIS scientist. He will have his session. He will give the... yeah.
My request is that these points are perfect unless they are linked to the XRF, this particular, when they're saying thickness issue. Who does this? This is done by hall markers? Yes. Until all the users, right? Particularly for a jeweler like us, almost 70% of the jewelry hallmarking is done by hall markers, right? And until I understand that, this will remain in an academic dream, and the BIS will come, they will talk about the standards, right? So there are two extremes. But most important in the entire triangle is hallmarking. Unless they come and say, yeah, I'm asking simple question. Do they have a standard on this? They can say yes, no, don't know. Yeah. Okay, yeah, thank you. Yeah, okay, thank you.
India also, BIS also has already published a standard, not been put into practice because of certain reasons.
On XRF, ISO standard is also there, IS standard is also there. And then the guidelines are also there for especially on hallmarking.
So,
yeah, 1 minute. Chetan want to say something.
So basically, we are few hallmarkers over here, Mr. So we can answer your questions after we finish this thing, one-to-one, or you can ask us in the session also, next session. Yeah, thank you.
so I presume that there is some multiple. Yeah. Okay, so there is an answer to that. Good. All right. I haven't talked about this because I skipped over it, but basically we have this is a constant, this is the intensity, this is the matrix correction that we just skipped over. It's there. We're not going to talk about it because it's not that important right now. But what is important is this S term, which is the specimen sample preparation. That is important because you all have to have the same preparation. In milled samples, this is for those of you that have to deal with powdered samples, you have to mill it to a certain amount. We compare it to a fused bead, which is, again, we don't have to explain it, otherwise it gets rid of all the particle size bit. That's considered a proper answer. If we don't grind it enough, the particles are greater than 75 microns, we're going to have big differences. because the particle sizes interfere with each other. If we grind it finer, then we get better results. We homogenize it, and everything has an equal chance of being analyzed. Another way to look at it is before milling, there are two bits, the blue and the red, and they're all mushed up, but they're not equal sizes. If we, after milling, we make them equal sizes, then we can get then the X-rays can interpolate or interrogate a representative sample that's homogeneous, and we won't have those problems. And then we can press them together. Over 15 tons of pressing, you remove some of those particle size effects. So the idea is to make things the same. Whether your standards or sample, make them the same. In precious metals, ideally we want to take it from a molten state. And here we have somebody taking a dip sample from molten gold in here. This comes from the Royal Canadian Mint. And this is something I witnessed quite a bit over the last 30, 40 years. What is interesting is we want to make sure we cool it quickly. If we don't, we get large grains. And impurity elements can form along these grains. They are not homogeneously distributed. We want to cool it fast so that we have small grains where everything is evenly distributed. If you don't, you're going to have problems. So we have different ways of preparing it. We can press it, we can cut it, we can lathe it, mill it, grind it, polish it, all sorts of things. You can do it manually or automated. You may even have to have a smooth surface on top so a suction cup can pick it up and put it in an X-ray. There's all sorts of variations. The main thing is it all has to be the same. For example, if you have a coarse polish, this is not for scale, this is just for illustrative purposes. From an X-ray point of view, compared to if the X-ray detector is here, coarse polishing pushes the sample away from the material, from the bulk. It actually pushes it away, so you're going to have a systematically low bias compared to a flat surface. So by all means, you can do coarse polishing so long as everything's coarse polished and it's the same. If you switch them up, you're going to have differences because the samples are pushed up differently from relative to the flat surface. Right? This is a gross exaggeration, but it illustrates the point from an X-ray point of view to the detector, it's different. So the main thing is to have the same thing, flatter the better. And you have to have it be consistent. You have to have it minimize your grinding strength. Flatness, burrs can cause problems. Contamination. You have to make sure you're not contaminating your sample with something else when you're doing your surface prep. You have to assure yourself that you're not mixing what you polish on one sample doesn't appear on the next sample, or your polishing material doesn't have something that interferes with your analysis. You have to do that kind of homework. Also, people, you have to be, and we'll get to that right now, you have to worry about surface contamination. Had we seen the previous slides, I would have talked about this. This is your sample. Let's say it's a silver gold alloy. If everything's lined up, it's great. But sometimes, what I discovered early when we first introduced it, people would be folding leads in fire assay and then go and work on the X-ray, and they'd have a giant thumbprint on the sample that was full of lead. So this bit of lead, our contaminant, suddenly we have 30% gold or lead in our sample. Where did that come from? It came because it's on the bottom of the surface, it's analyzed preferentially over everything else because it's closer, so you have to have a clean sample. So the sample surface contamination gives a false high concentration to that impurity. Make sure you're clean. Everybody's clean. This lowers the concentration of the elements, all the other elements in the sample, because the contaminant is measured preferentially. So clean the sample surface, clean your hands on that. So alcohol and water 50% dry, either by a clean cloth or air dry. Handle with the edges, not the surface. The sample prep standards and quality controls in the same way as the samples. No special, if you're not using a special surface preparation, you may have to make sure they're clean and analyze the same surface. No flipping forward. The back of the sample one day, the front of the sample the other day, always the same sample. That's very important. Quality control standards. You want to have something. Yes?
For sample preparation, I have one question. You have shown that cooling, that's a forced cooling, right? Quenched. You have shown one slide.
Cooling pattern.
Cooling part.
Cooled rapidly. It doesn't matter whether it's a coin or doré or anything.
I'm asking, the sample is quenched,
Yeah.
or what is the rate of cooling? It is very fast, or it is some air cooled, or it's what kind of cooling?
It will depend on how hot the sample is. Like
Let's say
water
1000 degree.
Water cooling would be the best.
Water cooling.
Yeah, where you quench it
So
first. If
will
you leave it air cool, it takes longer. If you keep it in the mold, it takes even longer.
But if you sudden cool that, will the crystal structure form?
The what?
Will the crystal structure will form?
It's going to form. It'll be small. You'll have small crystals. You won't have big ones.
Rapid cooling always produces finer grain size.
Yeah, that's fine. That's
Yeah.
fine. But that is not the requirement, right?
Like normalizing, annealing, water cooling. So water cooling is the best. The fastest cooling is water cooling. It gives a very fine grain size and good for analysis.
Yeah, it gives it it makes it homogeneous. They're all small. If you let it slow cool, you'll have larger grains. Impurities form at the grain boundaries, and you won't have a homogeneous sample.
But it's reflects from your crystal structure only, no? The X-ray reflects from the crystals only.
No. What happens? All right. If right here, if that's a long grain,
Yes.
okay, and I've got copper and lead, they will accumulate on the grain boundary edges there. Some will be homogeneous in the gold, but a lot of other things will accumulate on the edges of the grain. So
Yeah,
if you
but-
have, and then the smaller we make them, we chop this up, they're more homogeneous. So when you look at if this is your X-ray vision, well, this is the area your X-ray is looking at. It's going to see, right now, it's going to see a grain structure here and a grain structure here, but it'll be different in the middle here if it's a long grain. If it's small and really, and you look at it here, it's going to see a more averaged one. You'll get a better result.
No, but if I cool that, again those elements will be present, right? So I want to see the purity of this material. Exactly. So
Yes.
now for copper or other elements, there will be different refracting angles, right?
No. That you're thinking of X-ray diffraction? No, it doesn't matter what, it'll be a homogeneous sample.
These are not mechanical mixture where copper is different, where gold is different. These are homogeneous alloy of different elements. So it's a compound, chemical compound, right? The homogeneity is same throughout.
Oh, that's fine, but you want to say how much gold in it. So
Yeah.
how do you do with this X-ray?
Basically, what he's trying to tell, there is always a tendency when you cool a metal, certain elements segregate and get settled, like a heavy element will go to the bottom, the top surface will have light elements, so density difference.
No, that's fine, but I need to know purity, right?
Yeah.
Let it be there. Let it be there. I want in this how much gold is there. How do
You'll
I
get
know?
it if you let it.
Homogeneous, you'll get a correct result. But if you do not put
you-
in a correct sample, your purity will not be same at different places, you have different purity. And XRF will always give difference on the top something is there, bottom something is there, and this point is different, this point is different. It's going to
No,
happen.
no, but it has to cover all the area, right? Your aperture and the sample. Sample has to cover all the area of
I'm
X-ray, right?
happy to talk to you about this later, but I got to get going on this. So quality control standards, Spectro and all the other places make great instruments. But we want to make sure that we want to satisfy ourselves that everything is working. So we always want to run something that we know is good or the same, a quality control standard that's homogeneous and stable. This can be an in-house standard or a reference, whatever. Something that you have confidence in and you run for a long time. So this can be a normal sample or match the material here. The best QCs have something that it's in the middle of your calibration range, not one end or the other. So you want to run it at a set interval. The main thing is, the question is, how many samples are you willing to rerun if your QC is off? That's a big question. Most people run it start, middle, end of the day, or depending on how critical it is, every hour. That's a decision you will have to make. But but the main question is, how many samples are you willing to redo if your QC is off? So in the ideal world, this is our QC, the green line is your average, the blue line is the lower working level, high and low, and the red one is your upper and lower control level. If it's bopping along here between your blue, that's covering 95%, you're good. However, if it pops up out of this, you're in trouble. We can do something like this. It's sort of okay. It's not alarming anything yet. That's a dangerous situation. It's drifting. And you want to look at that on a daily basis and do something about it. What can you do? You can compensate via drift correction. And every company calls it a different thing, a monitor or drift correction. It can be the same, so long as it's the same, it's run at the same time you calibrate. And what it does, this is your original intensity, this red line. And after time, the X-ray tube gets a little worn, it loses intensity, so you have to rerun your monitor, and what it does is makes a correction factor that pops it back up here. And it will reset your account for any instrumental drift. If you drop your QC, if you use the wrong QC, put your hands on it, it can't correct for that. You have to do something else. You have to make sure your QC is correct. But overall, this is what you can do to correct for any instrumental drift. Plating thickness. We talked about if you have a thin layer of gold over copper, we measure the K alpha of the copper. So it's a reverse calibration. The smaller the gold, the smaller the gold plating, the higher the copper counts are, and as the plating thickness increases, your copper reduces. So that's what you can use that as a measurement. Use specialized software, calibrate with known plated standards are the best. That's very good for very thin coatings, and it's limited by the infinite thickness of your substrate, whatever gold. So basically with gold, you can do this provided the gold is an incredibly thin coating. As it gets thicker, then you can't do that. So people from Fisher will be talking today about plating thickness, and I think they can go into that. But that's
that is a limit. That's something that we can do. It's also something that you have to be worrying about counterfeiting. People can then cover tungsten with a thin coating of gold. Generally, counterfeiters put a flash coating of gold that's not that thin or not that thick. And if you see tungsten, you know that that's not right, or something else other than gold, then you know that it's not quite right. We have an example program here. There's a set of elements for that includes gold, copper, and another set that includes silver and palladium. And we can see that the yellow ones really give a better value for gold or for silver. Over here, in blue, the spectrum in blue is better for gold. So you would use the two programs to do that. And that gives just a closer view. I'm moving along. This is an XRF example, and we don't need that. All right, let's take a look. Accuracy. XRF is a comparative technique. Accuracy is dependent on the calibration standards or reference materials you have. You cannot, there are things, there's mathematical things, but ultimately it is, you have to have calibration standards to tell your programs what it's all about. All elements in the reference material must be determined with good accuracy and uncertainty by others. So you have to have the value plus your uncertainty to have an idea. If you're using fundamental parameters for your determination, all the elements in your sample have to be analyzed. Otherwise, you're going to get a wrong result using the fundamental parameters program. Keep track of your significant figures. Reference materials with 3 significant figures, your XRF values can't have any more than that. Just because the computer says that, spits it out, doesn't mean it's true. Calibration standards, it's a concentration plus an uncertainty. It must be homogeneous at the analytical surface. Sources purchased and made in-house, some surface, you have to have the same sample preparation so that they're comparable. And if you get new ones, you compare it to your trusted standards and to see whether you can rely on that or not. And I suggest strongly, given many of you will be using a small aperture, that you test your calibration standards that you have at different positions so that you know how homogeneous your material, your calibration material is at that level. Otherwise, if it's not homogeneous, if you move it off a little bit on one side, you may not be getting the value you want. And that is a problem.
Does the minimum thickness matter?
Yes. Yes. Well, we talked about the minimum thickness as being 6 microns. So it has to be greater than 6 microns. Better, if it's a ideally, you can get something that's a millimeter thick. It would satisfy XRF conditions, but I can't work with it. I've tried working with gold foil as a standard, and it's really hard. Yeah, about a coin, something about the thickness of a coin is much better. And if you're making your own in-house material, sample from the analytical surface. This is a standard I made, a silver standard, and I took the millings from that first half micron, and I took that shaving and I analyzed that to get calibrated values. Otherwise, if you take samples, shavings from this side, remember how thin, we're talking microns, it might be completely different. Enough that it matters for your accuracy. If you want good accuracy, analyze from take shavings from the surface that you intend to analyze. And also, if you're using small spots, like 2 and 4 microns, analyze it at different spots. Find out where it's the same, and find out where it's different, or within a tolerance that you can deal with. So that's the big takeaway from that.
And it does make a difference. All right. Where are we at? Well, we've talked about XRF, we talked about the physics, we've talked about the instrumentation in terms of energy dispersive, we've skipped matrix effects and calibration, we've talked more about the practical applications. So we've covered most of it that I think is important to you. I'd be happy to talk to you about wavelength dispersive otherwise, but we have to move on. If you're interested in more, well, the XRF spectrometer vendors do offer courses. They are more focused on how to operate their software with a bit of theory. And certainly if the people from XRF vendors, I think that their practicality is that they want to teach you how to use the software and throw in a bit of theory. Other courses like our XRF group and ICDD offer courses that teach you the theory. Doesn't matter what the instrument is, we teach you, you learn the theory, and it's just then you can figure out how to use your software to get the results you want. There are books, there are 3 that I can recommend. The first one is available through Australia, unfortunately, and the last one is, again, very good books, but they're only available through Malvern Panalytical, so a little bit harder to get to, whereas the general text on analytical analysis that I've co-authored and I've done the XRF section is more detailed than my lecture here, and it can provide you with more information. That's more readily available through DeGrudo. Yes?
Can you just explain more about the courses, the duration, how do you take it? I'm just inclined towards this one.
Well, the ICD course happens in Philadelphia in the US once a year. The LXCG, they may be, a few days ago I found that the 2 groups are combining to provide a course. However, the London X-ray Conference is certainly open to doing customized courses for people. Sorry? This is offline. Some of it can be done by Zoom meetings. We've done Zoom courses online. It's not as good as being in person, but it can be done.
Fisher has every Monday. There's a big series going on with Fisher.
Oh yeah?
Every Monday they have online. Courses half an hour. Courses is free, available to
Oh really? Neat. Yeah. And last, I'd like to acknowledge Pankaj Deshma, Ankur Goyal from MTC PEMP for inviting me, and the Indian Gold Conference for having me, LBMA, my colleagues from the London X-ray Consulting Group, and lastly, Ishma from Nucleus Analytics, who's going to be showing you some things right now. And lastly, you for your attention, and thanks very much. All right. Are there any, we've had a lot of questions. Are there any other ones? A lot of this is because in terms of accuracy, it's really how you make your standards and how you characterize that, and how the samples you present to the XRF. If they're curved, if they're not flat, then that becomes an issue.
Given all ideal conditions, everything is okay.
Yeah. Yeah.
Okay. What is the maximum accuracy? I mean, what best accuracy you can achieve with XRF as compared to other methods?
Okay. I can't answer for gold, but I can answer for silver. I converted a program when I first started using XRF. We used the Gay-Lussac method to determine silver and sterling silver, which is a back titration method, and it had an accuracy of 0.03 fines. XRF had the same accuracy and slightly better precision. And we were counting for about 60 seconds with a wavelength dispersive instrument. Counts are important for accuracy and precision. So you can get it all depends. If you get low counts, then you have to count longer. If you have lots of counts, then you don't have to count as long. So it is capable of, gold refiners use X-ray to determine silver for settlement. They don't use it for gold because there's too many interferences and the amount of gold that is interrogated by the X-rays is too small. But they use that information for fire assay so that they can get a better estimate or be more accurate. If you're only analyzing 22 karat gold and you're interested in gold, then it's much easier. If everything, say, if it's alloyed, if the gold is alloyed with silver, then you can make standards to bracket that, and you will have better accuracy. How much? That is up to your sample prep, how long you count, all those other things. So I can't give you a number, but you will get better accuracy if you bracket around that with your standards. And then you will have to make your comparison between fire assay or whatever method you're currently using, whether that satisfies it's sufficient for your X-ray. That's when it can do the best result, when you have few impurities and a very narrow range. You can get good results. If you then want to apply this to Dore, which is like that, it'll give you an estimate. Yeah, it'll give you an estimate to help you with fire assay, but I wouldn't want to trade on it. So does that give you some context? A lot of this is what you're prepared to do. I can't answer that because I don't have your equipment or your standards. You have to make that judgment. And you have to do the work ahead of time to make those determinations. The more work you put up front in making your method and you're making your standards, the easier it will be later. If you don't, then you're going to have, well, how come you didn't do this? How come you didn't, then you're going to have more questions. You will still have questions, but you'll have fewer. Anyway, I hope that gives you some context. Yes?
In India, we face a big challenge in terms of which XRF to select.
Yes.
So, like, there is flush of cheaper XRFs which are coming, and we are like not able to judge which XRF to take. A lot of things coming from China, and we know that certain detectors or XRF. So how do we determine that?
You have to have a set of calibration standards and unknown samples. You take them to each vendor, and you test them. And you compare apples to apples. But you have to have your own calibration standards. Don't rely on them to test theirs. You have to. By the way, before you get an XRF, you've got to get your calibration standards already. Don't rely on somebody else to supply them for you. Otherwise, you're going to get fooled. So then you have to do the work in comparing the same calibration samples, the same unknown samples, and see which one works best for you. Not only in terms of accuracy and precision, whether you can use their software, whether it gives you the quality control that you want, whether it can do the drift corrections. I had some vendors' software, I can look over here and I can know exactly what my samples are doing. Others, I had to kind of go up and look. That is a judgment that you have to make as to what works for you. So there's several factors. You have to define those ahead of time and make the comparison. Again, the more work you put in initially, the better the result. That's my experience.
That's correct.
Yeah.
I prepare my own samples, which have been tested, proved. Those samples I took it to the manufacturer and I said, please compare your result with mine. So that's why whichever equipment is made, if you have your own standard samples, it is much better rather than relying on the equipment.
Yeah. And that, even when I had comparing to ICP standards or evaluating an ICP or Flame AA, I gave them everything. Calibration standards that I prepared, I know. Otherwise, you're relying on their ability to make calibration standards for your, that's not going to work. You're the expert in your own samples. So you make those, even with solution standards for other instruments, and you'll have a better result. All right, any other questions? Yes?
What is the best method to determine the uncertainty of the machine? We have only input from the CRM. There is no other defined parameters to define.
Well, the other one is how long you're going to count for, your counting time. Because there's an instrumental uncertainty, and that's
yeah, we have challenges in determining the instrumental uncertainty, especially.
yeah. Well, you know what your standard is,
Yes.
and there's several ways of doing this. You can do duplicate measurements.
Is there any
The same sample measured twice, and you can keep track of that, and that will give your measurement, your instrument uncertainty. If you're measuring the same sample for the same time, over time you'll get a difference, and you can take the square of the difference and sum it, and take the square root of that divided by the number of replicates, and that's your instrument uncertainty. So that's another way of getting it. For a set counting time. Okay, can we take a sample, one of your calibration standards, and measure it in 4 different places? Yes, sure. And we'll see what the results are. Okay. Okay, so it's a
Here you can explain the uncertainty of the standard.
yeah. So it's a 75, 22, 18 carat?
18 carat.
Yeah. So with these elements in it, silver, copper, nickel, zinc, they have a set uncertainty here. And so we're looking for those elements.
Yes.
And if we can take 4 different positions
Okay.
and take the average and standard deviation of that?
Yes, sure.
Okay. Like, can we do that?
Time.
Yeah?
You can set the time. Like.
Oh, can we do 15 seconds? Let's make it.
Yeah. Longer the time.
Now, is that on the same spot or different spots?
This is on the same spot.
Okay. 10 samples, we're seeing a standard deviation of 0.2.
Yes.
Okay, let's see if what we get here.
Yeah, this is the actual value.
Yeah.
This is the actual value.
Yes.
75.10.
Mm-hmm.
And the uncertainty is a 0.11.
Yes.
Like here we got 75.09.
0.9. But the standard deviation is double that of the standard uncertainty.
Yeah.
Yeah. Okay.
So I can do the measurements in the multiple spot now.
Yeah.
So I'll take one spot. Okay. I'll take one here.
Yeah.
This is multiple measurements.
Oh, so it's doing 5 replicates
Yes.
at that spot, and it's going for a minute? It's measuring for a minute?
Yes.
Okay. So,
The K lines of rules.
yeah. One of the things you'll notice here about the background is there isn't any background. It's pretty flat. That's because it's a metal sample. It doesn't have much scatter.
Yeah, this is the energy line 8.02
Mm-hmm.
of the copper K line.
Yeah. Okay, so we should have a value now. Where is that? Okay. Will it record the next one? Okay. Okay, so we've moved it to a different spot.
What is the effect of time? You said 15 seconds.
The precision of the measurement, you're going to get uncertainty due to what they call counting time statistics. If you want to improve that by a factor of 4 or 2, you have to count 4 times longer because it's a square root function. Counting time matters, but to improve it, you have to count so much longer to improve it. So, and that's just for the measurement uncertainty of that, of those peaks. The higher the count rate for the peak, the less uncertainty it is. Because remember, we're just counting photons, and by that, it's an averaging process. Okay, second, so we're close. It's full close. Silver there's more variability because it's a lower concentration. All right, so let's take another spot, and we can get a standard deviation from 3. 4 would be better. It depends on how long we want to, how hungry everybody is.
We want to give it a try using the actual jewelry also, part of the sample.
Yeah. Well.
See how they do it, right? Because there are different spots that you're showing.
Yeah. Well, okay, first of all, let's clean it. You've just handled it, so we should clean it with a cloth.
Oh, okay.
Because that will affect the measurement.
Should we do that?
Yeah. Here, do you have or maybe on yeah, fine.
And a part of the jewelry is rhodium plated.
Is what?
Gold also, it's a rhodium plated.
Oh, it's a plated gold. Well, that'll be interesting.
That's what you showed also in one slide.
Yes.
You showed also, right?
Yeah. Yeah. Well, that plating will vary depending on the curve. Like for coins, if the coins are plated, the edges are thicker and they go into a. So as your jewelry bends, the plating will vary depending on the bending of the material.
There's a question from Zoom.
Yes.
From people who are attending online. How much deeper X-ray penetrate into the sample?
It depends on what element and what the sample is. The examples we've talked about are gold and silver in a gold matrix, or a silver or a copper matrix. Depends on what the element you're interested in and what the material of the sample is. Those are the 2 criteria. So I'm afraid that's a depends question. Depends on what that person has for an answer.
Thank you. Any more questions? We are just running out of time. Maybe
Yeah.
this is the last trial, and after that, we can conclude this session. As we wait for the result, any questions at this point in time?
Okay.
Yeah. First, we will
can we-
interpret this result. Yeah.
Can we get a standard deviation for that? 3, 4. So we're getting the same standard deviation as we got for 10 samples, 10 replicate measurements at the same spot. We've done 4 replicate measurements at different spots, and we're getting the same standard deviation for gold. That's not bad. I mean, ideally we should do the same number of replicates, but on the first. Oh, beg your pardon, parts per thousand. So it's quite good. Good. The certificate value is 0.1 uncertainty, so we've added there's more uncertainty due to the measurement compared to the certificate. And that's what we'd expect because we're measuring. So, and it's 75.10. What did we get? 750.7. So there is a bias there. The question is, can we live with it? There's bias in all the measurements. All measurements have bias. All measurements have imprecision. It's just a question of whether we can live with that or not. And that's not my quote. That's from Michael Thompson from London. So
It's okay? So, we
So,
conclude?
for those who are interested, we can do 4 measurements or 3 measurements on this chain and see what the standard deviation is. And this is a 2 millimeter, 1.2. Oh boy, very small.
And you have not done any preparation of the sample?
Other than cleaning it with a cloth. Yeah, yeah. Yeah. And we don't have any lead here too.
So, whatever be the result it is, how do you look at it? Because we have not done any surface preparation.
Let's find out what the variability in the material is. Let's do an experiment. Find out, and then we can see whether we can live with that or not. Okay. Okay. So let's find another spot. Okay, we want it to cover the aperture.
You locate the spots on your own, right? On its own? You are just template. Okay.
Now you see, if we hadn't covered the aperture and gotten only half the sample, we would get a completely different result.
So we should expect a different result here?
Don't know. We're going to find out. It may not be the same.
Generally, it happens at the joints.
Yeah. And if you can see, there's a solder mark there, so that will be completely different. So the question is, what do you pay out on? Because there's soldering joints there.
Of course, it doesn't take that.
Yeah. So the question is taking that 4 or 3 replicates on those type of samples representative of the whole thing? No, because it doesn't include the sample, the soldering. So you'd have to have an estimate of the area or the volume that your solder takes up and sample that the same way and combine them. And that's hard to do. What would be the best way of doing that? Melting it and take. Okay, so.
But the standard deviation has changed, right? Earlier it was 0.3, now it is 0.6. How's that?
Well,
the mean comes the same.
The mean.
Yeah, so it was now.
Yeah, so you're.
Also, but the SD was 0.3.
Okay, but the standard deviation is 0.6.
But earlier it was 0.3, but the mean was same. How is it?
The average, there's the average.
It may not be same. Last time it was only one sample.
Yeah, so there's no average there. It is just the single measurement.
No, the other point here, the other spot on the chain, it was 0.3 SD. Now it is 0.6.
You have added one more sample.
Yeah, and by the way, taking a standard deviation of 2 samples,
So
although
average,
just because the computer will allow you to do it, it's not valid. You need 3 or more to get a standard deviation.
Thank you.
So there's more variation in this sample than, and we haven't even talked about what the soldering area is. So that's a problem for a jeweler to deal with evaluating your sample. Again, the best way would be to melt it all down, but of course then you don't have a chain anymore. So in that way it is a destructive. To properly sample it, it's destructive. Anyway, I hope this has given you some insight. We have clearly there's probably way more questions than we've given you answers for. Hopefully we've given you some thought, but a lot of it is taking the time to do your work on your calibration standards and your QC standards so you understand what your error is. The more work you do up front, the easier time you'll have later on. I think with that, I'll leave you. Thank you very much for your attention.
Thank you. Thank you, Dr. Mike Hinds. Mr. James Jose, we need your presence for 1 minute here. Mr. James Jose is the President of Federation of Hallmarking Association of India. Please come and kindly felicitate Dr. Mike Hinds. Please. Sir, please come on the stage. Here, come in the center. Yeah.